Okay, in this video, I would like to start with uh, Euler-Bernoulli beam theory. This is the first one that we are going through in this series. This is video 2 after having the introduction related to the index notation and rotation matrix. So if you have not seen that video, it would be helpful to listen to it and watch it. Okay, so here I would like to establish some introduction here. Let's say we have I will do any beam, but let's say for the example we have a cantilever beam. This applies to any boundary condition that you might have, and some loads are applied on this beam. Obviously, the beam will deflect, and this deflection is something that we would like to calculate, as well as the bending moment, the shear force, the shear stresses, and possibly the slope of the elastic curve, which is the deflected curve. We call it elastic curve. And so on. However, in doing that, usually we use the Euler-Bernoulli beam theory, BT here. Sometimes it is referred to technical or engineering beam theory, or sometimes even don't refer to any theory, but most of the textbooks on solid mechanics uh, and also strength of material refer to this as a beam equations, equilibrium, or just follow the calculation. We want to dig into this and see what kind of background assumption is there, and uh, basically put the foundation for going further if we need to increase the accuracy of the beam theory, which is the Euler-Bernoulli beam theory. Okay. Having said that, we come here and establish a coordinate system always. So I come here and establish my x along the axis of the beam and my z downward. So basically what I have here is a coordinate system that, following right hand rules, will give me z, and y is outward, and in x, y, z the rotation or the moment is positive counterclockwise. Basically z goes over x. This is the positive direction according to right hand rule, because if you use right hand rule, your thumb will point towards positive y. It is always recommended to have a established coordinate system when you are dealing with beams or any other continuum mechanics type of problem. Okay, so having this coordinate system, we come here and look at more carefully what's happening here. Let's say any point on this beam, and this is basically the axis of the beam. The beam can have a cross section. Maybe I draw a cross section, doesn't matter what shape. For our discussion, let's take a rectangular shape, and this beam is shown here, a kind of a zoom section shown here. Obviously, this is my x-axis, and this is my z-axis. So x-axis is normal to the plane, the cross-section plane. Z and y are in the plane. Okay, so now any point, and this is the neutral axis, say, which goes through the centroid of the cross-section and shown here. So assume this line here as the axis of beam uh, aligned with the neutral axis. Now, any point on this axis uh, will have some displacement due to the applied load. We call the displacement of any material point ui, which is a vector, and it has component u1, u2, u3. For this treatment, I will follow the map that I explained in the first video, video 1, and that is, I called it kinetics map. So we start with displacement, which is the first thing in kinematics. Now, let's say if I have some applied load here, any kind of load, doesn't matter. This beam will deflect downward in the xz plane. So therefore, our u2, which is any displacement in the y direction, is 0. So all of the beam points will move in the xz plane. Now, in terms of the u1 and u3, let's, for the simplicity, I equalize it to u, 0, and w. And we would like to find out about u and w. Now, in general, these u and w are function of, could be function of x, y, and z. Well, we are saying that all the deflection and transformation and translation, whatever any material point on this line for now, or any material point on this face or section of the beam, will have only displacement or translation basically in the plane, which is the YZ plane, and its normal is in the x direction. Okay, let's look at the W first, actually. So W is say deflection, that could be translation, that could be warping, that could be out of plane warping, could be rotation, anything when basically this point comes to the new position that we have here. So basically this point is represented by this surface here. So in general, W could be a function of x and z. However, in Euler-Bernoulli, assumption is this, that this cross-section translates without any deformation in the z direction. It means that any point on this surface or in this cross-section will move as a translation. There is no internal strain or deformation. So if you like, if I want to explain this better or more clearly, so if I have a material line here, maybe I use another color to show this. If I have a material line here, let's say this material line when the beam is in initial position and deflected position will have the same length, the same, and there is no stretching or contraction in the plane. So that means that W is only a function of x. At any given x, let's say this is given x, this point, the, the cross section translates to a new position in the z direction. So that is the first assumption. This implies the first assumption that planes perpendicular to neutral axis remain plane after deformation. So in a way, you can say that the plane in this direction acts as a rigid body. So it's kind of you move a plate, which is kind of can be considered rigid, and you move it in the direction of your deflected beam. So if I can draw here, maybe in a miniature way, uh, I can say that this plate moved here in the z direction. So that takes care of z direction. We know that we don't have any out of plane in the y direction. There is no displacement. Now let's look at u. U is the displacement of any material point in the x direction. That needs some attention and some explanation. But another assumption of Euler-Bernoulli is that planes normal to the neutral axis remain normal after deformation or deflection. What does this mean? To summarize here, these are two major, let's call it major assumptions in Euler-Bernoulli beam theory. Obviously, these assumptions are constraining the degree of freedom, or shall we say, deflection of the beam. Okay, so let me maybe zoom a little bit down here and show you what I mean here. So there are two related to this assumption, there are two quantities that need to be considered. Schematically, if I have my beam, we are considering a cantilever beam for sake of discussion, and we don't mean to by any chance be exclusive to this cantilever. It applies to any beam with any boundary condition as long as you assume the Euler-Bernoulli uh, theory. So if I have a cross section here initially, and I am basically looking at this cross section as a side view. So my point of view is normal to the y direction. So I am looking at this from the side. So it is a line. So this is my, and after this beam deflected, so I draw it. After this beam deflected, then this normal, and I use another color here to be distinct. Maybe I bring this guy down. So this is transferred here or transported here. As we said, just it comes down in a z direction without any stretch or contraction. Now, here it is perpendicular to the neutral axis. And the second assumption that we have for Euler-Bernoulli is that plane remains normal after deformation. This is obviously not normal to this deflected curve or deflected elastic curve. So what should we do? We should come here and rotate this plane, cross-section plane. Maybe I extend it a bit here so I can show. Rotate it such that this becomes normal at the point, at the x point along the x-axis. So this is local treatment. This doesn't mean that applies to all the way. At any point this applies, but obviously the amount of rotation will be different. But at this x point, let's say, let me call this x so we are clear what we are talking about here. This is x. So at this x point, I have to rotate my transported or transferred cross-section, translated, shall we say, by certain angle such that it becomes perpendicular to the deflected elastic curve. That is a very key point here. And I pause a few seconds here so you can see what is going on. Now, we call this angle, let me maybe, we call it phi. We call it phi. Another assumption or kind of side assumption is this, that we assume that deflection etc. is small for applying Euler beam theory. In other words, the slender ratio, which is the length of the beam over a typical cross-section area, let's say, I don't know, B, for example, and that is, to be clear here what we are talking about, this is the length. B is a typical cross-section dimension. Could be the width, could be a typical cross-section. This is, if it is larger than 20, then this assumption that we already discussed will bring about 1% error to deflection. As you will see, these two assumptions hugely simplify the calculation. And 1% is not a high price to pay for it. But if this ratio goes to, basically, if your beam becomes deep, or your length becomes a small, short, or deep beam, say around 10, then your error is 3 to 5%. And if it goes to 5, then your error is about 15 to 20%, a big percentage. So we cannot apply this theory to short beams, and I will discuss why this is right. But most most of the beams that we use in engineering, typical beams, not a specialized beam, uh, if it is laminated beam, that's another story. Maybe we have to use the higher order beam theory. But most of the beams, we have 5, 6, 7 meters of length, and the typical dimension is order of centimeters, 10, maybe 20. So this ratio applies here. Now, therefore, here what I wanted to say is that uh, uh, the angle phi is very small. If this angle phi is small, I will look at the magnitude of what happens here. So maybe I draw this in the same color. So this material point here will move in this direction. So basically we have transferred the cross section in the z direction and then rotated by phi. So this will be my u, x or u. Since phi is small, then I can say that this is my z coordinates from the neutral axis. Therefore, u, or say magnitude of the u, I will talk about the sign convention very carefully, and I have not seen this treatment in many books. When it comes to the sign convention, it's kind of sliding through, but I will try to make it very clear what actually happens for the sun. So I use absolute value. So the magnitude of this displacement is what? Is z y. For a small angle, we can say that this length is the z, which is the distance from neutral axis, times the angle in radian, of course. Perfect. This is one thing, and maybe I should put magnitude of the on these two, because these two could have a sign. If you are above, for our coordinate system, if you are above the neutral axis, your z is negative. If it is below, your z is positive, and phi has a sign that I will discuss. But before going into the sign discussion, uh, let's look at the other quantity. I said two quantities. This is one of them. The other one is actually the slope. So I will redraw this. So not to crowd the picture here, I will redraw this and explain the slope. So if I have the same beam, same elastic. So at any point, I have a slope. So at this point, the slope is here, the slope is here. And since this is W, we said that this is W. So the slope is dW dx. Let's call it theta. Again, I would like to call it the magnitude of this guy, because I would like to separate the magnitude and sign convention for clarifying very clearly what are these quantities. Now, for the second assumption to be true, we should have, so let me write it here for the second assumption, or maybe I should say the second assumption implies that magnitude of dw dx is equal to phi, right? Because it is very simple geometry that if you have a, this is say neutral axis, this is your plane perpendicular cross-section plane, and if this rotates by theta, let's call this theta, by theta, the magnitude, then this should also rotate by theta. Right? So this is your new orientation that I showed here with orange, and this is the new elastic curve. So if I want to label these things, elastic curve, original axis, this is elastic curve or slope, this is the cross-section, original cross-section, this is the rotate. So now this line is perpendicular to this line. And that's only that this was phi that I defined. This phi should be equal to theta. That's a requirement, geometrical requirement. So basically, if we summarize here, in Euler beam theory, any point, any cross section at any given point along the axis of the beam will move down as a rigid plate or plane, shall we say, as a rigid plane, and then rotate by the amount of slope at that point. Let me repeat this again. In Euler beam theory, a cross section at any given location along the axis of the beam will be moved in the direction of the deflection, in the z direction, as a rigid surface, and then rotate by the amount, by the angle which is equal to the slope at that point. I hope I could mention this fact very clear. I haven't talked about the sign yet. All of these things are absolute values yet. I haven't talked about the sign yet, and I will quickly and shortly. But this is a very major realization in Euler beam theory, which, as you will see, will simplifies the thing, but of course, it will bring inconsistency also. So Euler beam coordinate system, I will go through sign convention, and I am basically following, maybe I can reorder here. I'm following the kinetics map. So this, if I establish my displacement, then quickly I can go to strain and stress and complete the problem. Okay.